Welcome to this lecture. Today we are going to study about microcanonical ensembles. So first of all, what are ensembles? Ensembles are a collection of large number of macroscopically identical but essentially independent systems. So macroscopically identical means the systems constituting the ensemble have the same macroscopic parameters, that is pressure, energy, volume, temperature, number of particles, etc. And they are independent systems. That means the systems are mutually non-interacting. Okay, so there are three types of ensembles: microcanonical, canonical, and grand canonical. So let's start our discussion on microcanonical ensemble. So in microcanonical ensemble, the energy, volume, and number of particles are constant. So microcanonical ensembles are a collection of large number of systems which are essentially independent systems, and energy, volume, and number of particles are same. Okay, so for this system, these are isolated systems and are also called closed isolated systems, but practically the systems cannot be completely isolated. So in microcanonical ensemble, the energy remains in the vicinity of E, and it is in the range from E minus half delta to E plus half delta, where delta is very less than E. Okay, and here the probability is 1 upon omega. The entropy is equal to minus kb pi ln pi upon gi, and for non-degenerate particles this will be equal to minus kb pi ln pi. Okay, so next, the partition function is equal to omega, and the density function is constant, and there are no fluctuations. Okay, so since it is a here energy, volume, and number of particles are constant, so the number of microstates will be a function of energy, volume, and number of particles. And we can write that for energy, okay, and also E1 plus E2 is equal to total energy, which is constant. Okay, so from here we can differentiate this, and we will get del omega 1 upon del E1 into d E1 plus del omega 2 upon del E2 d E2 will be equal to 0. Okay, so now if we divide both sides by omega 1 into omega 2, we will get 1 upon omega 1 del omega 1 del E1 plus 1 upon omega 2 this will be equal to 1 upon omega 2 del omega 1 del E2. Why? Because from here we can write that dE1 plus dE2 is equal to 0, that is dE1 is equal to minus dE2. Okay. So next, from here we can write, okay. So in thermodynamics, we have seen this relation that PdS is equal to du plus PdV. Okay. And in statistical mechanics, we will add one more term. Okay. And the thermodynamic entropy is related to the statistical entropy by this relation. Okay. So from these two relations, we can write that these we can simplify to ln omega is equal to 0 implies that 1 upon kb del s del e is equal to, sorry, this is constant, so this will be a constant, and let's say we denote it by beta. Now from this relation we can write 1 upon t is equal to del s upon del u at constant volume and number of particles, and here the energy is basically the internal energy. So from this relation, putting it in this expression, we will get that beta is equal to 1 upon kBt.